In this video I'm going to give you a very quick overview of how to estimate an ARIMA model for a data set. In order to do this, I've created an artificial data set whose parameter values I know in advance, so I can check how well my procedure is fitting a model to the data. This is the data generation process I've used. I've taken a variable x, and x is determined according to this equation, where delta x equals 0.5 plus 0.3 delta x t minus 1 plus a random error term ut, where ut is normally distributed with mean 0, variance 1, and where the covariance or correlation of ut with its own past values is equal to 0 for all values of k not equal to 0. So this is an example of an ARIMA 1, 1, 0 model. It's integrated of order 1 because it's expressed in differences here. So the x series contains a unit root, and that must be differenced in order to create a stationary series. Secondly, it's autoregressive because it contains one lagged delta x t minus 1 on the right hand side of the equation. And finally, it's got no moving average components, so the final part of the ARIMA specification is 0. So we have an ARIMA 1, 1, 0 model here. The other thing to note is the presence of a constant or drift parameter in this equation, 0.5 here, which will ensure that this series has a stochastic trend. It will generally slope upwards because we've got this constant term in our equation. So what I've done is created an artificial data set based on this data generation process using the random number generator in eViews. And I want to see if I can take the data for that series and identify the model correctly, identify the stochastic process generating the data. Remember, a useful place to start is always to plot the data series first. So if I type in here plot x, this is the data set that I've generated, and you can see that it's basically upward sloping because of the presence of that drift parameter, but that there's a certain degree of randomness in it because of the random error term u. Okay, so I want to identify the stochastic process generating that data. The basic tool I'm going to use to do that is the parallelogram. So the first thing I'm going to do is type in the command show x here and then look at the parallelogram. So if I go to view parallelogram, this is the parallelogram of my data series. And you can see that it follows the classic pattern of a series that contains a unit root. The autocorrelations start off high and decline down fairly slowly to 0. Also, we can see they seem to die down along a straight line rather than along an exponential curve, which would be the case if we had a stationary stochastic process. So there's definitely a unit root present here, and that means that the first thing we should be doing is difference in the series. So let's take a look at the first difference of the series. If I type in here show dx, okay, and then look at the parallelogram of the first difference, then we see the parallelogram here looks very different. The first order autocorrelation is still significant. We can tell that because if we look at this Q statistic here, then this is a test for the significance of the autocorrelation up to order 1 in this case. The p-value here is very low. So we have a significant first order autocorrelation. We can also see that because it lies outside these standard error bands here, and we look down and we see that all the other autocorrelations are within the standard error bands. So as a first attempt, I'm going to fit an AR1 process to my data. So if I shut down this window now and estimate my equation, so I'm going to regress dx on a constant and a first order autoregressive process, AR1. Hit return and it estimates my equation for me. Now remember, when we've estimated our equation, we still need to go back and check whether or not we've accounted for all the structure in the series. And to do that, we look at the correlogram and the residuals. So we go to View, Residual Diagnostics, and look at the correlogram here. And we see here that the residuals of this equation have a very flat correlogram. None of these autocorrelations lies outside the standard error bands. So by difference in the series and then estimating a regression with an AR1 component, we seem to have accounted for all the structure that's present in the X series. Okay, so let's go back to our equation and take a look at it. So if I click on Stats here, this is my equation, and remember this has been generated through a known data generation process. The constant term, or the drift parameter, that I specified was 0.5. Well, the estimate is 0.7, but that's well within two standard error bands of the true value, because you see the standard error is 0.14. So although it's a little bit away, it's not significantly different from the value that I chose. The AR coefficient was 0.3 in my equation. Well, my estimate is 0.3084. That's very close. So I do seem to have recovered the data generation process reasonably well using this approach. I've got the correct variables in my equation. The parameter values are actually pretty close to what they should be.